Hello everyone, I'm Dr. Brad Musil and welcome to Lecture 5 of Logic and Critical Thinking. This lecture is on truth functional logic, or what is also known as sentential logic or propositional logic. So in this lecture we continue our discussion of deductive arguments. We'll discuss another way of sort of representing what's being said in a deductive argument, and then the truth tables that we'll be discussing will enable us then to assess these deductive arguments, much like we used Venn diagrams in the rules method to assess deductive arguments in the last chapter, or what we talked about in the lecture 4 video. So much like the last video, there's a lot going on in this lecture. We'll have to unpack a lot, but I keep mentioning this, right? It is one of those things I think that with practice, these truth tables, it seems very daunting at first, especially if you've never done anything like it. But again, with practice, you can become pretty comfortable with them. At least we won't be messing with any more than, say, 3 claim variables on the homework and the quiz. So really, it's pretty manageable once you get kind of, again, used to how it all works. Much, again, like the Venn diagrams that we talked about in the last lecture. And much like the last lecture, I also have additional lessons. So while I'm thinking about that, I want to mention that I've provided additional lessons, so I'll have links for those at the bottom of this video. But additional lessons are what I've called extra lessons for lecture 5, where I go in and we'll talk about in much more detail these various topics that we'll discuss more generally in this lecture video here. So I have extra lessons, 4 of them for this lecture. Extra lesson A is on the basics of truth functional logic. So one of the things we'll talk about here at the outset are the basics. What is truth functional logic and what are the main ingredients, if you will. And in that extra lesson A, I go into much more depth with respect to that. Then extra lesson B is on the 4 basic truth functional symbols and their related logical operations. And so we'll again touch on that in this video, but if you need extra help or something's still a little fuzzy after you watch this video, take a look at again that extra lesson B, where I discuss again the 4 basic truth functional symbols and the corresponding logical operations. Then extra lesson C is on symbolizing compound claims. Okay, that's something we'll develop as we go on. What do we mean by a compound claim? But it's basically just something, right, that has 2 different parts, at least 2 different parts within it, right? That's a compound claim. That's actually what we refer to as a conjunction. More on that as we proceed. But again, extra lesson C then gets more into how to go about symbolizing the more difficult claims, the more difficult compound claims. And then extra lesson D, arguably the most difficult thing that we'll be doing in this lecture, in this chapter. By the way, this corresponds to chapter 10 of the textbook, edition 13, if you were taking the course. Again, arguably one of the most difficult things we'll be doing in this lecture or in this chapter is constructing and then using truth tables to assess these deductive arguments. And so extra lesson D is 45 minutes long. It goes into a lot of detail in terms of how to do that, and I provide a lot of examples. So if you are struggling with truth tables, which many students find themselves struggling with truth tables, at least initially or early on, definitely go check out extra lesson D then. Okay, so I wanted to mention those extra lessons. What are we going to be up to in this more general lecture? Well, we are going to cover all those things I just mentioned, but not with the depth that I will go into in those particular extra lessons, right? So we'll touch on the basics. We'll go through and talk about the main ingredients, plain variables, truth functional operations, and their corresponding symbols, and then also the idea of truth tables and what exactly is going on with those. We'll cover then these truth functional operations and symbols in a little bit more detail, go through and talk about the 4 main ones we're going to be wrestling with: negation, conjunction, disjunction, and conditional. We'll talk about some common argumentative forms. Oh, before that, we'll actually talk about expanding truth tables as well, like what to do if things become a little bit more complicated, or you have more than 1 or 2 claim variables. How do you go about constructing the truth table accordingly? So we'll get into some of those nuances. But then, like I was saying, we'll get into some of the more common argumentative forms as well: Modus, Ponens, Modus, Tollens, and then also some of the respective common argumentative forms that are fallacies, right? Because they're what's the word? They're common because their underlying form is very similar to the valid ones, as we'll see, but there's a slight difference, and that's all it takes to then render the underlying form invalid as opposed to valid. So we'll go through some of those, affirming the consequent, denying the antecedent, and so on. We'll go through some of those common underlying fallacious forms. Okay, we'll talk about then, we'll end by discussing truth tables in more detail and kind of going through how you go about using a truth table to assess, deductive arguments, which is really our main goal here, right? We want to be able to take something that's said and figure out whether it's any good, right, from the logician's perspective. And so specifically here, we're again dealing with deductive arguments. Okay, I guess we're going to go ahead and transition then. Oh, I did want to mention, got a new board finally. I've mentioned this in a few different videos. Did get a bigger board, so hopefully this helps for you guys in terms of being able to see what I'm actually doing, especially given my terrible handwriting at times. But we'll go ahead and dive in then to the lecture itself. As I was intimating a moment ago, right, we are dealing with, again, deductive arguments, okay? Something that's said in a deductive fashion that's meant to be taken, at least, or that we might take in a deductive fashion. In other words, it's the point that we've been hammering home throughout the course up to this point, right? What do we mean by deductive? The conclusion of the argument is at least thought to, right, necessarily follow given the premises. And so what we're going to be talking about is another way to represent something that's said, right, a deductive argument that's offered, to represent that and then be able to assess it. Okay, so that's what we're up to here. This time around, what we're dealing with is called truth functional logic, as opposed to categorical logic, which was discussed in the last lecture. As I think I mentioned earlier, truth functional logic is also sometimes called propositional logic or sentential logic. It's propositional if you think about it in the sense that the things we're discussing, specifically these, so we'll have claim variables, right? We'll just be dealing with letters that represent claims. The important thing is that these claims, that these claim variables represent, those are things that can either be true or false, right? So they have that quality about them, right? That characteristic that they are either true or false. Okay, that's important, and that's the sense in which what we're doing is propositional, or we're dealing with things that are propositional. Right? Someone is saying something that can either be true or false, and then given that, we're going to represent what they're saying and try to analyze it accordingly. Okay, so hopefully that made some sense. Just trying to get into why sometimes this is referred to as propositional logic. They're proposing something that can either be true or false. Okay. Let's talk a little bit more about these main ingredients here. So this is slide 2, by the way, of the lecture notes. So I mentioned, what we're talking about in general, truth functional logic or propositional logic or sentential logic. So what are the main ingredients? I would say they come down to these 3 basic elements. Okay? These are the 3 basic elements of what we're going to be talking about. Okay? Claim variables, truth functional operations, and their corresponding symbols. So what do I mean by that? Just negation. So our first example is right here, by the way. So of a truth functional operation, and then its corresponding symbol, how we're going to symbolize it. Okay? And then our other main ingredient that we will be working with throughout this lecture then is this idea of a truth table. So we'll explore that here in a moment. So what do I mean by claim variables? Okay, as I mentioned in the middle of slide 2 there, they're basically letters that signify claims. So the upshot of what we're doing here, right, is we're taking something that's being said in an everyday sense, and we're going to translate it into what I call logical notation. In other words, what results is no more than basic claim variables and truth functional symbols, right? So we take the average everyday sentence, Joe will go and Susie won't, and what we come up with will just be basic claim variables. Okay, and logical operation symbols. Okay, so these are claim variables, and then these are, truth functional symbols, right? That represent the logical operations that are going on underneath what the person's saying, right? What's being implied in terms of logic, right? The relationship between these claims. So Joe will go, but Susie won't. That's the average everyday sentence that we begin with. And what we're going to translate it, a part of our job then, we want to translate into something, right, what I call logical notation, where it's just these claim variables and these truth functional symbols, which represent, again, those underlying truth functional operations that are at play. Okay, so in this instance, for this example, right, J represents Joe will go, and S, you have to be careful here, represents Susie, I think that was the name I gave her, will go. It's not Susie won't go, right, which was what was said in the everyday sense. When we're dealing with basic claim variables, we get rid of all the operations or the symbols. Those are separate, right? When we're talking about the claim variables, it's just Joe will go, Susie will go. That negation, right, what's involved with the person saying, but Susie won't go, that's going to be indicated by then that negation symbol. And we also have a conjunction. We'll talk, this will make more sense as we go through the different examples of these truth functional operations, and then of course their symbols. But we actually have then two different operations at play, reflected by these two logical symbols. But our two basic claim variables are J and S, and they're representing the basic claims that are at play here. One, Joe will go, and two, that Susie will go. And the person saying, this will be the case, right, but this won't. Okay? And that's represented via logical notation by this. Okay? And so this, well, this is representing Joe will go, but Susie will not go, right? Which was our original sentence. So Joe will go, but Susie will not. Okay, if that's our, if that's the original sentence we started with, okay, then this is what it will result in when you translate it into logical notation. So there's the average everyday sentence. This is then what it looks like in logical notation. The claim variables are just J and S, and they represent the basic claims. Joe will go and Susie will go. Okay? And then we also, in this instance, given what's said, we have two different operations at play, represented by these two corresponding logical symbols of conjunction and negation, right? Because this person originally made kind of two distinct claims, right? They're saying two things will be the case. Joe will go and Susie won't go. And that's represented by this conjunction symbol. Okay? They're positing two distinct things will be the case. And then also, part of what they're doing is negating one of the basic claims that Susie will go, right? They're saying Susie won't go, and that's represented then by that negation. Okay, so hopefully it's just starting to kind of come across, right, what's going on here, what I mean by claim variables. Again, claim variables are just the letters, J and S in this instance, that represent the basic claims at play. And then the truth functional operations, in this case, it's conjunction and negation, right? Those were implied by what's being said originally, and then we represent those operations with these symbols. Okay? So conjunction and negation was implied in what the person said in their original everyday sense, and so we represent that in our logical notation with the conjunction symbol and the negation symbol. Okay. So as I mentioned on the bottom of slide 2, we'll flesh out truth tables in much more detail at the end of the lecture, essentially later. But for now, right, we still want to have like a general idea of what's going on in a truth table. As they point out on page 487 of our text, they say, quote, a table, what is a truth table? It's, quote, a table that lists all possible combinations of truth values for the claim variables in a symbolized claim or argument, and then specifies the truth value of the claim or claims for each of those possible combinations. And that sounds like a lot, somewhat confusing, but hopefully, again, it'll become clearer as we proceed here and give examples. I'll go through and give some examples of truth tables. Actually, I'll provide them as we go through with each of these logical operations as well. Speaking of which, let's go ahead and actually just go ahead and move on and start doing that. So moving on to then our discussion of these basic truth functional operations that we're going to be dealing with, given things that people say in an average everyday sense. Right? There are certain logical sort of relationships that are implied given what they're saying, right? And so we want to go into 4 of the, I would say by far the most popular sort of operations, if you will, and then their corresponding symbols. So that's what we're up to here. We're going to start with negation, which is slide 3. Okay? So what's going on with negation, as I indicated at the top of the slide, is basically the contradictory of whatever the claim was to begin with. So, right, if we start with D being dude goes, okay, in this case, my example here, and we had a little truth table here, if we only have one claim at play, as we do in this particular scenario, then we only have two possibilities. Dude goes could be, which is represented by D, could either be true or it could be false. Okay, so we have two possibilities. Now, we want to know, well, what about this idea of dude won't go? What if somebody says, dude won't go? Hopefully it's spelled out in a little bit better English than that, but dude won't go, they say. Okay, well, this is basically just the opposite then of that original claim. So it's going to be true in every instance that the original claim was false, and it's going to be false in every instance in which the original claim was true, because it's positing the opposite. So if dude goes is true, then dude won't go is going to be false. Okay? But if dude goes is false, then dude won't go, well, that's going to turn out to be true. By the way, I should have started by mentioning this. So this is a truth table, right? And these ones and zeros, okay, I much prefer 1 instead of a T or spelling out true, and a 0 instead of a capital F or an F or spelling out false, because it's very simple, very clear. And if you don't use those, let's say you use T and F, well, I mean, is that a T, is that an F? That's what I call a TF, and it would be counted wrong in your homework. So I would encourage you instead to, what is that, an F or a T? I don't know. Wrong, right? Give me a 1 or a 0, it's much clearer, okay? Now, if you have really good handwriting, it's a moot point, but I don't. And so, much clearer, I know exactly, what's true and what's false here, okay? So hopefully the truth table makes sense for a basic negation here, right? If dude goes is true, then dude won't go, which is what's being implied by this logical notation, that's going to be false. But if dude goes is false, then dude won't go, or it's not the case that dude goes, is going to be true. And I should have mentioned that. So either one of these symbols works for negation, right? So instead of this, I could have done this. Okay. That's one of my graduate instructors actually preferred this and always used this. But either one of those symbols works, okay? And that reads something like, it's not the case that D. If you were to read this kind of in logic speak, if you will, or logical notation, it would read something like, it's not the case that D. Okay, okay, so that's negation. Fairly straightforward. By far, I would say the easiest of these basic 4 that we're going to discuss. Okay, next, I'll go ahead and this. We'll get into conjunction. So this is slide 4. Okay. I can never make this symbol. That's why I use that symbol for a conjunction. Okay. So we're talking about a conjunction here. So this is the top of slide 4 as the authors of the textbook define conjunction. It is as follows from 307, quote, it's a compound claim made from 2 simpler claims called conjuncts. A conjunction is true if and only if both of the simpler claims that make it up, its conjuncts, are true, end quote. So what it looks like, and well, we had one up here, right, is basically keeping it simple. That's the symbol. You could write the ampersand instead, right? But that's what it looks like in logical notation. So let's say this actually was a good example, right? But let's say somebody said Adam and Ben will play today. Okay? There's actually 2 distinct claims being made here. 2 distinct things that can be either true or false, okay, if you analyze this properly. On the one hand, Adam can play today. That can either be true or false, right? And then Ben can play today. That can be true or false as well. So either of those things can be true or false individually. Hence, there's two different things being posited. That's the idea behind a conjunction. Okay? So when you go to analyze it then, so for example, when you're representing it in a truth table, so we have A and B here. Okay. Now we have more than two possible scenarios, right? Because, and this gets into how to construct your truth table. I get into go into that in much more detail in the extra lessons. But I always like to start on the left side, and however many rows you have, in the case of two claim variables, you're going to have 4 rows. It's always you will divide that by 2 and start with that many truths. So I'm talking about the far left column. So true, true, and then it'll be the opposite for the last half. So false, false. Okay. And you always want to be as neat as possible when it comes to these truth tables. Otherwise, especially if you have bad handwriting, it's really easy to get these things together. If you don't have lines, I mean, it can be really hard to interpret your own table. So be careful there. And then to represent B, the column B, it'll just be every other. The far right column is always going to be true, false, true, false, true, false, all the way down. So true, false, true, false. Now, if you step back, what have we done by doing this? These are called the reference columns of your truth table, by the way. They represent just the basic claim variables with no logical operations involved, right? So the truth and false combinations of truth and false truth values for the basic claim variables are represented right here, right? They could both be true. A could be true, or B and B could be false, or A could be false and B could be true, or they could both be false. But we've represented every possible combination. So going back to what was originally said in everyday, parlance or language, Adam and Ben will play today, right? It could be the case that they both play today. It might be the case that Adam plays today, but Ben didn't. It might be the case that Adam doesn't play today, but Ben does. Or it might be the case that this person was really wrong, right? And neither one of them played today. Okay. So to be able to put this up on the truth table, we have to first get the basic claims that are involved. Okay. And then now this person who's telling us this, Adam and Ben will play today, they're saying confidently. Right? To assess or analyze that entire claim or that compound claim, right, whether it's true or false, everything they've said, right, Adam and Ben will play today. How do we assess whether that's true or false? Well, whether that's true or false is going to depend on the truth values of the individual parts within it. That's why we call what we're doing here truth functional. It hinges on the truth values of the constituent parts, right, that comprise it. Okay, so for a conjunction, you kind of want to memorize this basic sort of rule. If you think about it, when is a conjunction going to be true? It's only going to be true, okay, if both things are true, both of the conjuncts, right? So Adam, so I should write this as a key. A means Adam will play today. So big, this board is so big I can't even reach the other end. And B is Ben will play today. Right? And this person is suggesting both are the case, right? Not just that Adam will play or that Ben will play, but the both things will happen. Okay? So for that to be the case, right, for us to suggest, okay, what they said was true, both those have to be the case. If even one is false or not the case, then what they told us as a whole was false. Okay? Because they're suggesting they'll both play. Okay. So they both have to be true. Both conjuncts, both sides, A and B, of the conjunction have to be true in order for it to be true. Otherwise, it's false. So it's hard to make a conjunction true, you might think in the back of your mind, right? They both have to be the case. Okay, so in this first row, when Adam does play and Ben does play, okay, well then Adam and Ben will play today. That's true as a whole. But in the scenario where Adam plays but Ben doesn't, well then Adam and Ben will play today is false. Okay, because Ben didn't play. Same thing when Adam doesn't play. That conjunction, right, that thing as a whole, that compound claim is false. And if they're really wrong, as I suggested earlier, if neither one of them plays. So it takes a lot, you might think in the back of your mind, to make a conjunction true. Both those conjuncts have to be true. Otherwise, it's going to be false. And that makes sense, right? They're committing to two different things. It's going to take more to make that true than just committing to one thing. Okay. Moving on to slide 5, we'll go ahead and tackle then disjunction. Disjunction, okay. So we represent this by a lowercase v. It's pretty much universal. So let's say our average everyday, what kind of average everyday sentence would be interpreted as a disjunction? Something like, either Adam or Ben will play. Okay, again, we have a compound claim. This person is saying something, two different things that might be true or false, right? Or what they're saying reflects two different things that might be true or false, right? We need to know something about whether Adam ends up playing or whether Ben ends up playing. Okay, so again, this is a compound claim. To be able to analyze whether this is true or false, we're going to need to analyze, right, the underlying truth and false values, if you will, or the underlying truth and false values of whether these constituent parts were true or false. God, I didn't say that right, but whether this as a whole is true or false, right, is going to hinge on whether the disjuncts end up being true or false. So, like we had in conjunctions, we had the left and right conjunct. Here we have the left and right disjuncts, okay, A and B, okay, and the truth or falsity of the entire compound claim is going to hinge on, right, the truth and false values of the individual claims that comprise that compound claim. So this is slide 5. As they define a compound claim on page 307 of the text, quote, as they define a disjunction. It's, quote, a compound claim made up of two simpler claims called disjuncts. A disjunction is false if and only if both of its disjuncts are false. So this one's interesting in that it's very similar to a conjunction, but it's kind of the opposite. So in the back of your mind, just remember it's very difficult to render this false, a disjunction false. Remember how it's hard to make a conjunction true because both sides had to be true? Well, it's kind of the opposite with the disjunction. It's hard to make it false because as long as either side is true, then the whole thing they suggested is going to be true, right? Because they're only suggesting by what they're saying here that one or the other will be the case, maybe both, right? But they're not suggesting both will be the case, right? But one or the other at least will be the case. Okay, so it's not as much of a commitment you might think of on the part of the person saying this as the person that's committed to a conjunction, right? They're saying both will be the case. Here, this person's just saying one or the other will be the case, perhaps both. So what are the basic claims? So basic claim variable, we'll have two of them, A and B. The basic claims are Adam will play, and then Ben will play. Okay, so we have two basic claim variables. So like the conjunction, we'll have 4 rows for our truth table. So remember when we only talked about with negation, we only had 2 rows because we only had one underlying claim at play. Whenever we have a compound claim with 2 or more, we're going to have at least 4 rows, right? And we'll get in, again, how to kind of determine the number of rows in a little bit here. There's a formula. But basically, it's going to double anytime you add another claim. Okay? So we started with just 2. It could be true or false when we had just 1, right? Throw in another one, now we're going to have 4 possibilities. 1, 2, 3, 4. Okay? If we throw in a third one, which we will here in a little bit, then we're going to need 8 rows. Okay. Also, keep in mind the difference between a row and a column. I know way back in the day, I had to learn that. We all had to learn it. Okay? Don't confuse or conflate rows with columns. Okay, rows go horizontal, left to right. Columns are up and down, top to bottom. Okay, so again, a disjunction is, quote, a compound claim made up of 2 simpler claims called disjuncts. So here we have A and B being our disjuncts. A disjunction is false if and only if both of its disjuncts are false. end quote. So it's going to take a lot to make it false. So putting up our truth values for our reference columns, same as it was for our truth table for conjunction. True, true, false, false, and then every other here. Okay. So there, again, we've represented all possible truth value combinations for the underlying claims comprising the compound claim. Okay. And we want to now be able to assess the truth and false nature of the compound claim based on whether these constituent parts are true or false. Okay, so is it the case that either Adam or Ben will play when both Adam and Ben play? Well, yeah. Okay, well then it turns out what they said was true. What about when just Adam plays but Ben doesn't? Well, then it was still the case that either Adam or Ben will play. Right, so that we say that was true. Okay, what about when Adam doesn't play but Ben does? Well, what they said, just think about it intuitively, right? They tell us either Adam or Ben will play. Ben plays. What they said was true. What about when neither Adam nor Ben play? Then and only then can we say, hey, you said either Adam or Ben will play. That was false. Because what you promised did not happen. Neither one of them ended up playing. So hard to make a disjunction false, right? Both of the disjuncts have to be false. As long as one of them is true, then what the person suggested is true as a whole. That's a disjunction. Finally, we'll move on to arguably the most difficult, and that is what's known as a conditional. It's difficult just because it's kind of weird. I don't know, it's not as intuitively obvious like when a conditional is true and when it's false from a logical perspective. But we'll go into, I think my example will help kind of illustrate why it is the case that a conditional is much like a disjunction is hard to render false. Okay, so this will make more sense here as we proceed. So we're talking about a conditional, and this is the example I use in the extra additional lesson, but it's just a good example to help illustrate the point that I was just referencing, how the sort of tricky nature of these. Let's say I said, if I win the lottery, I'll give you $1 million. Okay? So someone says, in everyday sense, if I win the lottery, then I will give you $1 million. Okay, this is again a compound claim because there's two constituent parts that can be in themselves true or false. All right, we have this idea of me winning the lottery, or I win the lottery. That can be true or false in and of itself. And then I give you $1 million, right? That separately can be either true or false. So if we were representing this, let's say W for win the lottery. I win the lottery. And then how about N for I give you $1 million. Okay. So how would we represent that in logical notation? So we have our basic claims here represented by our basic claim variables. So we're going to use W and M to represent, right, what's being said here. And then we need an arrow to represent the idea of a conditional, that underlying logical operation known as a conditional. Okay, so it's going to be, what's said here is going to look like this then. Okay, and we need to talk about two fancy words known as antecedents and conditionals. Do I have that on here? Yes. So this is what I mentioned at the top of slide 6 as well. Okay, this is what's known as the antecedent. Okay, the first thing before the arrow in a conditional is known as the antecedent. It's prior to the arrow. Okay, and then this is what's known as the consequent. Okay. So in a conditional, you have that antecedent and the consequent. The idea is Here's how I would encourage you to think of a conditional from a logician's perspective. Again, we're interested in how do I assess the truth and false nature of this as a whole. So the best way I would suggest to think about it is, when can you say you're a liar and you lied to me? Well, two things have to be the case, okay? And when it comes to a conditional, for you to be able to say you lied to me. The first thing, the antecedent, has to have happened, right? Because they didn't say anything would be the case if this didn't happen, right? They're saying something will be the case if this does happen. So the antecedent has to be true, okay? So from a logician's perspective, the implication of that is if it's false, if this doesn't turn out to be the case, we're gonna assess the whole thing as true from a logician's perspective, because we can't say you lied to me, okay? So to be able to say you lied to me, which is what we need to be able to say from a logician's perspective to label the whole thing false, this has to turn out to be true. Right? So the antecedent has to be true. And then what also has to be the case to say you lied to me is that they didn't end up, or I didn't end up giving you $1 million. So the antecedent has to be true, and this has to be false. Look, if I end up winning the lottery, so that's true, but then I also give you $1 million, you can't say you lied to me because I also gave you the $1 million like I said I would. The only time you can say you lied to me is if I win the lottery, right, and then I don't give you $1 million. Then and only then can you say, right, you lied, what you said as a whole is false. And if you keep that sort of example, that's always helped me in the back of your mind. Then I think approaching these conditionals is a lot easier and it kind of makes more sense than when you're sort of mapping them up on the truth table. So speaking of the truth table, let's use W and M here. So we're using two basic claims. So we know, again, we're going to have 4 total rows. This is the same as before, the last 2 examples, conjunction and disjunction, whoops. And then every other. And then we just need one more column. So you basically just have to commit to memory, the truth values for a conditional. It's only going to be false in one scenario, one instance. So again, a hard one to prove or to suggest is false, much like the disjunction. It's only going to be false when the antecedent is true and the consequent false. In every other scenario, right, the antecedent's false to begin with. So in this case, right, the antecedent's W. These 2 scenarios where I win the lottery didn't happen. What I said as a whole, from a logician's perspective, you render true. Okay, you can't say I lie. Okay? And then if I win the lottery and I give you $1 million, you can't call me a liar either, right? It's hard to call me a liar when it comes to conditional. Just like it's hard to call the person a liar who offers a disjunction. Both things have to end up being false for a disjunction, right, in order to call that person a liar. Here, the antecedent has to be true and the consequent has to be false in order to call them a liar and say what you said as a whole is false. Okay, so there's only one scenario in this, basic example where the conditional as a whole is false. In every other scenario or possible combination of truth values for those underlying claims, the conditional as a whole is going to be rendered true. All right. Okay, so hopefully that's starting to make some sense. I mentioned the same kind of rule of thumb in the middle of slide 6. They mentioned, I should say, I quoted them mentioning the same rule of thumb on page 308, where they say, quote, a conditional claim is false if and only if its antecedent is true and its consequent is false. So if it doesn't make intuitive sense to you, at the very least, if you can just memorize that basic relationship or rule, then it still shouldn't be too difficult. Right? Just remember, the only time this conditional is going to be false is if the antecedent is true and the consequence false. Otherwise, every other scenario, it's going to be true. Okay, let's move on to slide 7, where we're going to discuss now what to do in terms of more difficult compound claims where there's more logical operations involved, or what to do when we throw in extra claim variables or extra claims, more distinct things that can be true or false independently. Our table in all those scenarios, right, is going to have to expand either up and down because we've added additional distinct claims that can be true or false, or side to side we'll need more columns because we have more logical operations involved in what's being said. And either scenario, hence the title of slide 7, we're going to be expanding the truth table. So as I mentioned, the top slide 7, truth functional operations can work in combination, yielding a much more complex truth table. All right, let's go ahead and just get rid of almost all this. Give ourselves some more space here. Okay. So I'll give you an example. Ruth won't go. But Sarah will. Okay. So as I mentioned, how's that going to look? Something like this. I would, as I have on the lecture notes, also throw that in parentheses in there to make it clear, right, that it's because otherwise this could be construed as that, right? You're negating that whole conjunction, right? In which case this whole thing would be a negation, right, as a whole. That's a lot different than what we have, which is conjunction as a whole. Okay? So we do want to use parentheses properly. And it's very important so that we can, right, determine the underlying structure better of what's being said. Right? Switch those parentheses around, like I said, and that completely changes, right, the idea of what was originally said. This does not represent this anymore. Instead, it would represent, it's not the case that Ruth and Sarah will go. Okay, so, by the way, I should put this up here. So R equals Ruth will go. And then S equals Sarah will go. Okay. So this actually represents, it's if somebody said something like, it's not the case, or neither Ruth nor Sarah will go. It's not the case that that they won't both go. Okay. That's saying something different than Ruth won't go, but Sarah will. So we need to be very careful and use those parentheses accordingly. So going back to this slide, this is slide 7, and we have a couple different operations involved now. So our truth table is going to look a little, it's going to expand, right? In this case, it's going to expand left to right. We're going to add an additional column essentially. So we'll start R and S, our basic claim variables, and we have those possible combinations of truth values for the basic claim variables. Okay, now we need to start figuring some other things out. So we have that negation, which we remember how to do that. Okay. So when is it's not the case that R is going to be true when R is false. Okay, so if R is true, then it's not the case that R is going to be false. Okay, so we go to the R column to figure this out. So when Ruth will go is false, then it's not the case that Ruth will go will be true. Okay, so both these scenarios. And now I believe we're in a position then, right? So we had to throw on an additional column essentially. So now we're in a position to assess the conjunction as a whole. Because we have both conjuncts. Before we didn't, right? We had to get not the case that R to get our left conjunct, but now we have it. Okay. So when is a conjunction true? Remember, it's hard to make it true. Both conjuncts have to be true. Either one is false, the whole thing is false. So, boom, right away in this scenario, okay, in this scenario where R and S are both true, okay, then in that scenario, not the case that R is false, so the conjunction as a whole will be false. Okay. Same thing here then. Okay, in this case, the left conjunct is true. What about the right conjunct? It's also true. So in this scenario, both conjuncts are true. And what about the final one? The left conjunct's true, but the right one is not. So that's what our truth table would look like. Okay. When's it going to be the case that Ruth won't go, but Sarah will is as a whole true? Well, only when Sarah goes and Ruth doesn't go, right? That makes sense. Okay, but this is how we represent it then with our truth table. Okay, and that is how we would sort of adapt if we have additional, additional operations at play. Let's say they made it even more convoluted and said if, right, all that's the case, and then they threw in then yada yada yada. Okay. Well, then it would be get even more interesting, right? You throw in more parentheses, and then Quincy will do something, right? Quincy. And then we'd have, let's say just Quincy will go. Right. If Ruth won't go but Sarah will, then Quincy will go. Right? That's actually represented right there. And that whole thing becomes a conditional. Okay? So, which is indicated by these parentheses, right? This whole thing is on the left side of the arrow. And if that all is true, then they're saying this will be the case. Right? So in that case, we would actually have 3 claim variables. We would have to expand as well, going up and down, which I think I do with an example on the next one, which so I'll wait to go up and down for that example here. But hopefully you can see then how you can tweak these things, and then all of a sudden, right now we've got a third operation at play. We're going to have to add another column, and we had a third claim variable introduced, and another third claim at play, right? Quincy going. So we're going to have to expand it this way too. Remember, when you get a third one, it's going to double the amount of rows in, so we'll go from 4 to 8. So that is essentially the point, right? Doubling the rows and how that works, expanding up and down. I think that's essentially the point on slide 8. Yeah. Okay, so turning to slide 8, let's go through that example. So Ruth won't go, but either Sarah or Teresa will. Okay. So, yeah, you're going to need parentheses, as I've indicated in the middle, and as I mentioned on the last slide, right, when I made that example more difficult. Parentheses are very critical when things get more complicated, right? So parentheses in terms of the logical notation that you produce, right? Because that's going to help distinguish what the overall claim is, and again, where those parentheses are, that can completely change the meaning of what's being said, right? And whether or not that adequately represents what originally was said in everyday language, it's going to depend on where the parentheses are. As I suggested with that last example, when I switched around the parentheses, it changed everything. Okay, so here's the example on slide 8. If we were to translate this, right, we have Ruth won't go. Okay. So to me, overall, this seems like a conjunction, right? We have Ruth won't go, and then but, so it's another, either Sarah or Teresa will. Right. So overall, it's a conjunction. On the one hand, we're told Ruth won't go, okay, but Sarah or Teresa will. So within that right conjunct, there's actually a disjunction as well. Because this is the right conjunct, and it's actually a compound claim in itself. So again, much more complicated than the basic stuff we started with. So let's do our key. We want to be very clear here in all this. So R is going to be Ruth will go, right? We never include negation in our basic claims. Ruth will go, and that idea of negation then will be represented in a distinct column, right? Ruth will go, S will be Sarah will go, and then T will be Teresa will go. Okay, so we got our key, our basic claim variables. That's going to be RST, so we have 3 of them. RST. Okay, so again, I like to start, you can start on the right and just go every other, and then you just double it going to the left. I always start on the right or the left. I know there's 8 total rows, so it's going to be, half and half. Start, so true, 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 false, 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 false. You want to be neat, especially the more rows and columns you add, the more imperative it is that you use lines and really try to be neat because there's a lot going on. Okay, then we just half that, right? So true, true, false, false, true, true, false, false. And then the far right's always going to be just true, false, true, false, true, false, true, false, true, false, true, false, true, false. Now step back, just as we did when two claims were involved. If we step back and analyze this, this is representing all possible scenarios with these three basic claims involved. They could all three turn out to be true, okay? Ruth could have gone, Sarah could have gone, and Teresa could have gone. All three of them could have gone, right? Or just Ruth and Sarah, or just Ruth and Teresa, or just Ruth, right? So, or none of them, all the way down to none of them go. So we've represented all possibilities, and that's going to enable us to get to the specifics of what this person has suggested, right? And analyze whether it as a whole is true or false, you know, depending on whether these particulars are true or false. Okay, so what do we need here? First, we're going to have to let's try to get that left conjunct. So that's a negation. So that's actually pretty easy. We'll just do this. It's not the case that R, it's just the opposite truth value of R, right, as we've learned. So R is false, or true, the first four, so not the case that R is going to be false, the first four, and then it's just the opposite. Okay? So now we've got the left conjunct, but we need the right conjunct. So S or T. Okay? So remember, it's hard to call the person a liar that's offering a disjunction. The only scenario in which this is as a whole is going to be false is if both of these are false. So long as S or T is true, the whole thing is going to be true. So S or T, both are true, so this is true. S is true, so this is true. Okay. Because remember, what's being said here? Sarah or Teresa will go. Okay. They both went. Sarah went. Teresa went. So one of them went. In this scenario, both end up being false. Well, then that as a whole, right? That disjunction then would be false because neither one of them ended up going. Okay, here they both went, here one of them went at least, here one of them went, and then we have another instance down here where they both don't go. Okay. Now we're in a position where we can finally actually get to the whole thing because we have both our left and our right conjunct. So now we can represent the whole conjunction itself, right? So not the case that R and S or T. Okay, so remember, it's hard to make a conjunction true. It's easy to call them a liar because there's only one scenario where it's going to be true, and that's where both of the conjuncts are true. Hopefully I said disjuncts here and not conjuncts. I don't know if I said it right or not, but here, right, the conjuncts, it's the opposite relationship, right? It's a lot harder to say a conjunction is true because both of them have to be true. Remember here, only one of them had to be true. Here, both of them have to be true. Okay, so let's look at not the case that R. Look, all four of the first scenarios, this is false. So the whole thing is going to be false. Okay, now the last four rows, not the case that R is true. But what about S or T? So here we go here. Okay, they're both true in this scenario. They're both true here. They're both true here. But here, well, not the case that R is true, S or T was false. So that would be false. So we have, what we've done here is represented the truth value of what they're saying based on all the possible scenarios that could have played out, right? Ruth went, Sarah went, and Teresa went. Well, then what they said as a whole was false because they said Ruth wouldn't go, but Ruth did go, right? So if Ruth goes, well, then what they said as a whole is going to be false. When is it going to be true as a whole? Well, when Ruth doesn't go, okay, and when either Sarah or Teresa does go, okay. So in all three of these scenarios, one of them goes, right? And what do you know? In all three of those scenarios, the thing as a whole is rendered true. Again, hopefully that's kind of starting to make some sense. Slide 9 hopefully depicts the exact same thing I just put up here. Otherwise, that would be embarrassing. I believe it does. Okay, so we'll go ahead and move on to slide 10. This is where, right, I thought I even mentioned they give like the formula. Basically, again, you just double the number of rows based on how many basic claims you have. So with one, you just have 2 rows. With 2 claims, you'll have 4 rows. With 3, you'll have 8. With 4, how many will we have? 16. With 5, how many will we have? 32. Now, as I mentioned before, we're not going to deal with anything that complicated though. So on top of slide 10, quoting the authors as they point out in 310, basically the same thing I just mentioned. Quote, every time we add another letter, the number of possible combinations of T and F doubles, and so therefore does the number of rows in our truth table. So this is them summarizing kind of what we're up to here, as they say on 312. Quote, what our table gives us is a truth functional analysis of our original claim. Such an analysis displays the compound claim's truth value based on the truth value of its simpler parts. Okay, so when is that going to be true? Well, it's going to depend on the truth value of these simpler parts. Okay. So that's the sense in which it's truth functional. What we're doing is truth functional, hence truth functional logic. Real quick one to mention, as the authors detail as well in the chapter, necessary and sufficient conditions. So those are related to conditionals. So we have the idea of necessary and sufficient conditions. And they always signal a conditional. Okay, so a necessary condition, as I indicate in the top of slide 11, is something that has to occur for something else to occur. So, for example, I like their example on 314. The presence of oxygen is a necessary condition for combustion. In other words, what we know from this, logically speaking, right, is if there's going to be combustion, then there had to have been oxygen. So we can represent that with a conditional, right? We know that so we have oxygen is O, and C is combustion. Okay, or there is oxygen, there is combustion. Okay, it would be like the more general claim, if you will. Okay, so right, if oxygen is a necessary condition for combustion, we know that if there's C, then there must have been O, or oxygen, right? If there's combustion, since oxygen was a necessary condition for it, well, then we know oxygen must be present as well. So if combustion occurs, oxygen must be there. Okay, so in other words, a necessary condition, right, it's become the consequent of a conditional. So a necessary condition is a consequent of a conditional. Sufficient condition, on the other, so that's what a necessary condition is, right? That's an example. A sufficient condition, on the other hand, so this gets into slide 12, is something that will guarantee something else takes place, or something else will occur, or something else will happen. So it's something that, should it be satisfied, will then guarantee something else will occur. Okay. So their example on 314, being born in the United States is a sufficient condition for U.S. citizenship. So let's say be born in the United States, and then C is citizenship. Okay. So being born in the United States is a sufficient condition for becoming a citizen. So it guarantees that's going to be the case. So in this case, the sufficient condition is going to signal the antecedent of a conditional. We know that if B is the case, it's going to guarantee then that C will be the case. Okay. So again, when you know something's a sufficient condition, in this case being born in the US, that's going to signal the antecedent, okay, of a conditional. Hopefully that makes some sense. So that was slide 12. So what I want to do for the next 6 slides, what I think I'm going to do is I'm going to try to conjoin. So basically what I do in the next 6 slides is go through the So we're transitioning. We're going to discuss the most common underlying argumentative forms when it comes to deductive arguments. So in other words, these are common forms. So given common deductive arguments, if you were to dissect the underlying logical notation of what's being said, you would oftentimes come up with these same basic forms. That's the sense in which they're common. Right? We're going to go through 3 common valid forms and 3 common invalid forms. So that's what's going on in the next, excuse me, 6 slides. But then following that, I want to get into truth tables and how to use those to assess arguments. So I'm going to kind of conjoin them by, as we go through the 6 common forms, I'm going to kind of put them up here, and then as we go through the truth table stuff, I'm going to leave space down here to kind of show what the truth table will be for all of them down here. So that's my strategy anyway. Hopefully that made some sense there. So again, these are common underlying valid forms of deductive arguments. Okay, so the first one we want to talk about is what's known as modus ponens. Okay, its basic form, as I've indicated in the top of slide 13, is if P then Q, premise 2 is P, conclusion is Q then. As I think they pointed out in the book, this is sometimes also referred to as affirming the antecedent, because that's what premise 2 is doing. It's saying, oh yeah, that antecedent is the case. Okay, so, and then I give you an example. I'm actually not going to write that all out on the board here, okay? But the idea is, you could take anything that's being said, and if it has this underlying form, right, it's going to be valid, okay? Because this form is always valid. If these 2 are assumed to be true, this has to be true, right? We're told if P then Q, and we're told P. So if we're assuming these are true, and P is true, well then Q has to be true. Okay, so assuming the premises are true, the conclusion has to be the case. That's why it's valid, right? So it doesn't matter what you throw or map up onto this underlying form, it's always going to be valid. So I give you the example. If it's a dog, then it's an animal. Premise 2, it's a dog. Therefore, it's an animal. But I could say anything. If I am really smart, then you're really dumb. I'm really smart. Therefore, you're really dumb. And it doesn't matter how crazy the premises are. As long as everything maps up here, we call it valid. Now, it might be unsound, as we've talked about in prior lectures, okay, but it would still be valid if it has this underlying form. Now, the next one that I detail on the next slide, slide 14, very, very similar, except I don't know if I'm going to have enough room here. Okay, it's very similar, except let me finish my sentence there. Except we're going to switch around these 2 things. And it's so similar, that's why it's such a common fallacy, because it can oftentimes come across, especially in everyday language, as seeming to be valid, because it's very similar in structure to this. But instead of affirming the antecedent, we're actually affirming the consequent, which doesn't give us license then to infer P, which is the mistake. Okay, so my example on slide 14. So much like I just said, doesn't matter what you say, if it has this underlying form, it's going to be valid. Same thing applies here, except it's always going to be invalid. Doesn't matter what you say, if it has this underlying structure, it's going to be invalid. Take an intuitively obvious example, I think, right? The one I offer on the bottom of slide 14. If it's a dog, then it's an animal. If it's a dog, then it's an animal. Then you're told it's an animal. They want you to infer that it's a dog. You have nothing based on the premises to infer that, right? You were just told something you can infer about what if it was a dog, then you can infer it was an animal. But being told it was an animal doesn't give you license to infer then that it was a dog, right? That's why this is invalid. You can assume the premises are true, and this can still be false, as we'll see in the truth table of it here in a moment. Okay, so that's affirming the consequent. Next we have, turning to slide 15, modus tollens. And the way this one works is like this. Sometimes it's referred to as denying the consequent. So again, this is slide 15. So that's the underlying form. It doesn't matter. I guess it says valid, invalid, valid. It doesn't matter what you map up, as long as the underlying structure of what's being said in everyday sense has this underlying form, it's going to be valid. So I'll give you an example on the bottom of slide 15. If it's a dog, then it's an animal, and then we're told, hey, it's not an animal, then it can't be a dog. It's not a dog. That makes sense, right? If these are true, if it's true that if it's a dog, then it's an animal, and if it's true it's not an animal, then it's going to be true it's not a dog. Okay, that conclusion can't be false. That's why it's valid. Turning to slide 16, very similar to Modus Tollens, but we switch these two around. That's why it's a very common fallacy. Antecedent. So that looks like a Z to me. It's going to bug me. Does that? Oh my. Okay. Conclusion. I gotta stop. Okay. So that's the underlying form. Again, this one's always going to be invalid. Doesn't matter what is being said in everyday sense if it has this underlying structure. If P then Q, not the case that P, not the case that Q. If that's the underlying structure of what they're saying, it's invalid. Okay. Example I give you at the bottom of slide 16. If it's a dog, then it's an animal. And they say it's not a dog. And then they want us to infer, well, then it's not an animal. Well, that doesn't have to follow. Okay? Just because those original premises are true, if it's a dog, then it's an animal, and it's not a dog, okay? That doesn't mean that it's not an animal, right? That could still be false. It could still be an animal. It just wasn't a dog. So hopefully that one makes sense. And then we have chain argument. This one actually throws in another variable. That was the ones I used. Okay, this one will always be valid. Okay, and I talked about this on slide 17. So we're throwing in a third. I gotta remember that when I do the truth tables here, we're gonna need 8 rows ultimately to do all of these, because these last two will require 3 claim variables and hence 8 rows. Okay? But again, it doesn't matter what's being said in everyday sense. If it has this underlying logical form, it's going to be valid. Okay? I'll give you an example at the bottom of slide 17. Again, this is what's known as a chain argument. If it's a dog, then it's an animal, premise 1. Okay? Premise 2, if it's an animal, then it's alive. So based on those two things, then we can conclude if it's a dog, then it's alive. Okay, because we were told if it's a dog, it's an animal. If it's an animal, it's alive. So the conclusion is if it's a dog, then it's alive. And hopefully, I try to use ones that are kind of make sense intuitively to us to see, oh yeah, that makes sense. If it's a dog, then it's an animal. If it's an animal, then it's alive. Well, then if it's a dog, it's got to be alive. But you can throw out any, much more convoluted things that are being said, and if they have that, throw anything that has that underlying form. If it matches that underlying form, it's still going to be valid. And then the last one we want to discuss is what's known as undistributed middle. So we are dealing with 3 claims again. Okay. And this is always going to be invalid. And it's common because, again, very similar, right? All these invalid forms, whoops, have very similar structures, but there's, a slight difference, and that's all that matters, right? To make the difference between it being valid, right? In this case, these two are switched, valid and invalid. Similar underlying structure, okay? But there's enough difference going on here that this is invalid, right? Whereas this one's valid. Let me give you an example of what's known as undistributed middle. Okay, so here's an example of something that's said in everyday language that would have this underlying form and hence be rendered invalid. So if somebody tried to tell us, if it's a dog, then it's an animal, and if it's a cat, then it's an animal, so therefore, if it's a dog, then it's a cat. Okay, well, that seems pretty clearly invalid, right? I mean, again, trying to use intuitively obvious examples here, but they're not always that straightforwardly invalid, right? Sometimes when you're dealing with less intuitively obvious examples, it might not be as straightforward that it's invalid, and that's why it can be helpful then to be able to identify these underlying basic forms, because then you can be in a position to say with confidence, yes, it's invalid because it has this undistributed middle, this very common fallacious underlying form. Let's go ahead and start talking more in depth about the truth tables, a little bit more in depth. I mean, we've kind of discussed a lot of the things I wanted to mention already, but as I mentioned, I'm going to go ahead and sort of show you the truth tables for each of these. As I quote them on the top of slide 19. Recall once more, what are we ultimately up to? We want to know if these arguments are any good, okay? As they remind us on pages 325 to 326, quote, an argument is valid if and only if the truth of the premises guarantees the truth of the conclusion. Remember, that's why these are all invalid, because we can assume these are true, and the conclusion still doesn't have to be the case. It can still be false. So that is, continuing the quotation, if the premises were true, the conclusion could not then be false, end quote. So what we're going to do here is talk a little bit more in depth, as I mentioned, about truth tables, and also I'll say a little bit about what is called the short truth table method as well at the end. But I want you to be, I'm not a big fan of the short truth table method. I want you to be able to do the entire long truth table method, because it enables you to better see what's going on logically. There's something to be said with respect to the short truth table method, don't get me wrong. But for rookies and people just getting into logic, I think it's important to kind of be able to do the long truth table and to be able to understand what's going on, with that table and what we're representing with the table, and obviously then be in a position to say whether the arguments you're representing are any good or are valid. Okay, so as they say on the top of slide 20, what we're doing with these truth tables. Quote, we present all the possible circumstances for an argument by building a truth table for it. Then we simply look to see if there are any circumstances in which the premises are all true and the conclusion false. So more specifically, is there, with respect to the truth table, is there a possible scenario where the premises are all true and the conclusion is false? Okay. And we'll see that in these cases there will be a row where the premises are all true and the truth table and the conclusion is false. But in these there will not be. Okay? And so that will then be what enables us, using the truth table method, to figure out that these are invalid and that these are valid. So as I mentioned in the middle of slide 20, the idea is if you can't find a row, as will be the case in these three, if you can't find a row where the premises are all true and the conclusion is false, then you would render it valid. Okay? But alternatively, if you find at least one row, all you need is one row where the premises are true and the conclusion is false, you'll indicate that, right, with a little asterisk, or somehow indicate what row or rows. It might be several, right? Maybe this one also is a scenario where the premises are true and the conclusion false. Well, then you would label it invalid. Okay? So the bottom of slide 20 is the truth table for affirming the consequent, but I'm actually going to go through all of these real quick. Before, I want to make sure so this is going to be slides 20 and 21. And then the last thing I'm going to go ahead and diagram all these, and then the last thing I'll do is discuss and brief the short truth table method as well. So that's the plan of attack here. and we'll have almost everything we need using the same truth table to be able to do these. Okay, as we'll see. So want to remember we're actually going to need 3 ultimately. So I'm going to put all 3 of them up here because we'll need 3 claim variables for that one. So nice and neat. True, 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 false, 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 false. Bear with me. Almost done with these lines. Oh, it's a terrible line. Let's lower that a little bit. I don't know how lower that is, but that'll work. So divide by 2. True, true, false, false. Every other one. Hopefully this becomes like second nature, like it is for me at this point, once you do it enough times. Okay, so to analyze this, we've already got P and we've already got Q. So when you're analyzing these arguments of truth tables in your homework and whatnot, you want to be very clear about what you're doing, okay? And you want to label things as well, right? So look, our second premise turns out to be one of our reference columns. So we're going to say, make that clear, premise 2 is here. So we're analyzing modus ponens right now, okay? So we've got our second premise here. We've got our conclusion here, but we're missing this, so we need another column. Okay, so we're going to need if P, then Q. Okay. True, true. Here's an instance where the antecedent is true and the consequence false, so that's going to be false. Same thing here. True, 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 true. Okay, hopefully that makes sense why I'm doing that. Okay. So now we're in a position to step back and analyze this argument, right? Because I gave you examples of arguments about cats and dogs and animals that somebody could say to us, a real life argument, if you will, that has this underlying structure. And we want to be able to analyze the validity of the underlying structure of what they're saying. Is it in fact valid what they're telling us? Okay, so here's how we do it. We have to get the premises mapped up on our truth table and the conclusion. We have them all. So now we step back and we say we want to identify any possible suspects. And what I mean by that are any rows where both the premises are true, because that's one of the things we need, right? All true premises and a false conclusion to be able to say invalid. Otherwise, it's valid. So both true premises, but the conclusion's also true. So that won't render it invalid. Both true premises, but the conclusion's true. Both premises aren't true. Both premises aren't true. Both premises aren't true. Both. Okay, so we're not able to find a row where all the premises are true and the conclusion's false. Because each row where the premises were both true, the conclusion also turned out to be true. So that's why then modus ponens is valid. We can't find a row in the truth table where the premises are both true and the conclusion is false. But let's see what ends up happening when we analyze affirming the consequent. So we actually have everything we need already. In this case, though, first premise is here, and second premise, I guess that would have been the same. Second premise, though, is here, and then the conclusion is over here. Okay, so now we're looking for suspects, right, on these 2 columns. True, true, but in that scenario, the conclusion is also true. So we can't render the argument invalid with this suspect. How about this suspect? No, because even though both premises were true, the conclusion is also true. How about this suspect? Here we go. Row 1, 2, 3, 4, 5 gives us an instance where the premises can be true and the conclusion is false. So we know this argument's invalid. Are there any others that would tell us that? Also this one. So we would, on the homework, we would identify both those rows as indicating that the argument's invalid. Not the case. So these 2, the second premise isn't true. But both these rows show us why affirming the consequence is invalid. Okay. What about modus tollens? If P then Q's premise 1, I should have left that. We need another one now. Not the case that Q. So it's just the opposite of Q. Okay. And we need not P now. Okay. So it's just the opposite of that. Okay, so we're doing modus tollens. We have premise 1, premise 2, and then the conclusion. So we want to find suspects. In other words, rows where both premises are true. We have 2 suspects down here, but in both scenarios, the conclusion is also true. So this is valid. That's why modus tollens is valid. We can't find a row where both premises are true and the conclusion is false. What about denying the antecedent? So premise 1 stays the same, but then these 2 switch. So this one, okay, we need suspects. Here's a suspect. Look, this row is an instance where both premises are true and the conclusion is false. Same thing here. Okay. So again, here it's the 5th and 6th rows that suggest that denying the antecedent is invalid. Let's check out chain argument. So for this one, we need if P then Q. We have that, so that's our premise 1. We need if Q then R. So let's put that up there real quick. Remember, the only time a conditional is going to be false is if the antecedent is true and the consequence false. Not the case here because the consequence is also true. Here it'll be false. Okay, anytime the antecedent is false, the consequence is always true. We're good here because both are true. Here it's false because the antecedent is true and the consequence is false. Both these cases it'll be true because the antecedent is false. Okay, so that is our second premise. Okay, and then we need for our conclusion, if P then R. So if P then R, going over here, true. Here we have a false because the antecedent is true and the conclusion is false. True, another false. And then all 4 of these will be true because the antecedent is false. Okay, so we should be in a position then to analyze the chain argument. Can we find any suspects? Here's a suspect. Both premises are true, but the conclusion is also true. So that won't render it invalid. Not a suspect. Nope. Okay, suspect, but conclusion's also true. So still valid as far as we know. Another suspect, but it's still true. Same thing here. So we cannot find a row for chain argument where the premises are both true and the conclusion is false. We found several rows where the premises were both true, but in all scenarios, the conclusion was also true. Well, let's see what happens when we switch some things around. Actually, in this scenario, it's going to be slightly different. R then Q. So R then Q. I'm going to have to kind of work backwards here. So R is the antecedent. So whenever it's false, I'm going to go ahead and just put a true in here. Because we know anytime the antecedent is false, the consequent or conditional as a whole is true. But what about scenarios where R is true? Is Q false? Yes, in this instance. And yes, well, here, wait. Let's see here. Here it's true. Okay, because Q is also true. And then what about this one? Here it would be false. Because R is true, but Q is false. So the conditional as a whole will be false. So that was premise 2. And now we need if P then R. We have that one right here. So let's step back and see if we have any suspects. Row 1, both premises are true, but conclusion is also true. So we're good there. Row 2 is another suspect. Both premises are true and the conclusion is false. So we've already found a row that renders this invalid. Okay, another suspect, but in this case the conclusion is also true. Another suspect, also true, also true. So what is it? Row 2 tells us, right, that undistributed middle, anything with this underlying form is going to be invalid. So we've gone through, we've shown how we can use truth tables then to analyze and assess anything that has these basic common underlying forms and to show then why they're either valid or invalid. So hopefully that is making sense. Let's go ahead. So I mentioned on 21, right, you use asterisks to indicate which rows show that the argument's invalid, if any. Otherwise, you wouldn't have an asterisk and you would just say that it's valid. Okay, so let's go ahead and talk a little bit on page 22 about the short truth table method. So again, I want you guys to feel comfortable using the long truth table method, to know exactly how to do it, what's going on, and so on. But there is merit to this idea of the short truth table method, and what's required to kind of understand it is knowing what we're after here and what we're ultimately analyzing when it comes to the validity of an argument, right? Remember, what we're trying to do is find an instance, if it's possible, where the premises will be true, all the premises will be true, and the conclusion is false. So one of the sort of shorthand things we can do is just kind of knowing that, right, we can take some shortcuts. Well, what can I plug in without going through all these possible scenarios? Are there certain things I can just plug in as truth values to make the conclusion immediately false, and then just see what happens? Are there things I can plug in? Right, what would I have to plug in here to make this Q false? And in doing so, can I still render these true? And if possible, then that would, right, that it would be invalid. If you couldn't, right, trying to make this false, if you couldn't then also make these true, that it was valid. But the idea is you don't go through again and meticulously outline all the possible combinations. You start right with the conclusion, and you ask yourself, what truth value do I need to assign to Q in this instance to make this false, right? Because I'm trying to find a row, trying to see if it's possible to make this invalid. So what do I need to do to make this false? And in doing so, is it still possible then, using that same truth value? So in this case, I need Q to be false. Can I plug Q in being false? Can I still then make all these premises true? And if you can, you show what truth values need to be assigned to the claim variables, and you say it's invalid then, because it's possible to find truth values where this is false and these are true. Okay, but if you can't find any possible combinations of truth values for those claim variables that render these true and this false, then you would know it's valid. Okay. So I go through again those two basic steps. Figure out what you need for the truth value for the conclusion to be false, step 1. I go through these on the bottom of slide 22. And then with that in the back of your mind, that truth value for the conclusion to be false, keeping that consistent, then can you still render those premises true? So I'm going to give you an example here, the same one I have at the top of slide 23. I'm going to go ahead and just erase some of this. So it is premise 1, if P then Q, if Paul goes, Quincy will go. Premise 2, Quincy goes. I'll go ahead and even make the key up here for this. And then we conclude Paul and Quincy go. So he would be Paul goes. Q is Quincy goes. Okay, so as I point out, we know the conclusion's a conjunction. Those are pretty easy to make false. We can just make either one of its conjuncts false. So as I mentioned, what happens if we give P? So we have two basic claim variables here, P and Q. So is it possible to assign truth values to these, which will make the premises true and the conclusion false? So first, we're going to start with the conclusion. How do we make this false? Well, as I mentioned on the middle of, or bottom of slide 23, let's go ahead and see what happens when we make P false. So that'll make the whole thing false, because we know as long as one conjunct is false, the whole conjunction is false. Can we keep these being, the premises being true though, with a P having a false value? Let's see. If this is false, to render the whole thing true, it's already true, right? We know a conditional is true anytime the antecedent is false, so we're good there. P having a false value will keep premise 1 being true. What about Q? Well, we can assign any truth value we want to Q, because we didn't have to say anything about it before to render this one false. So we have come to, without depicting all possible combinations, I've already come up with possible combinations here where when you plug these values in, it's going to show that this is invalid, because these are going to turn out to be true and this is going to be false. Real quick, let's put that up here and show you with the long truth table method. Okay, all possible combinations. Okay, and we have P then Q. I'm going to do this pretty fast. Okay, true, false, true, true. Then we have our conclusion. So we have premise 1, premise 2, and then we want our conclusion, P and Q. Remember, both P and Q have to be true for the conjunction to be true. Okay, so step back. Now we've got put the long truth table out here. Are there any suspects? Okay, conclusion's still true. Ah, right here. We have our suspect. So if we did the long truth table, we would have also rendered it invalid. And lo and behold, what are the truth values of P and Q in this row? They end up being the same thing as what we determined they would have to be using the short truth table method. So that's an example of using the sort of short truth table method. What you have to have in mind to try to come more immediately, if you will, to figure out whether it's going to be valid or invalid. Okay, but again, I do prefer the longer truth table method, at least for you guys, just because then you can see everything that's going on. You can kind of notice relationships better, I feel like. So until at least you get really good with this, I would encourage you to stick with the long truth table method when you have an option before you go on then to the short truth table method. Okay. Is that it? I think slide 24, I mean, basically slides 24 and 25, I'm just going through, you know, the gist of what I've already talked about in terms of the short truth table method. That's, you know, 24 just goes through kind of the steps that we already went through there to figure out how using the short truth table method to make that invalid, or to show that it's invalid. And then on 25, it's talking about, well, look, if you can't find any such combinations where the premises are true and the conclusion, which would make possible combinations of truth values for the basic claim variables that would make the premises true and the conclusion false, then you know it's valid. And let me give you an example real quick of such an instance. So premise 1, if P then Q, premise 2, not Q. What is this, just Modus Tollens, I think? Not P. If Paul goes, Quincy will go. Quincy won't go, so we know Paul won't go, right? That's a valid form. We know that ahead of time, right? This is Modus Tollens. But let's try to do it using the short truth table method. So we know to render this false, right, we're going to need a certain truth value for P. We're actually going to need a true truth value for P, right? Because then the negation will be false. Okay, so if P is true, then not the case that P will be false. Right? So that's what we'll need P to be, we'll need it to be true in order to render the conclusion false, which is what we're trying to do to make it invalid, right? And if we can't, plugging in this truth value for P, if we can't then make these also true, we know it's valid. Right? So what happens, we have to assign P a true truth value. What happens then with the premises? Okay, well, if so we want to try to make these true, right? Well, if we have P be true, the antecedent, then the consequence is going to have to also be true. Otherwise, the conditional as a whole would be false. So that's going to have to also be true. So Q is going to have to be true. Well, what happens when we make Q true for the second premise? It turns out to be false, right? Because if Q is true, then not the case that Q, that's going to be false. So there's no way when we make this true when we make this false, there's no way to then also make these both true. And that's how we know it's valid then. Okay, so there's an example of, you know, trying to use the short truth table method where it fails then, right? You know, hey, this isn't possible. Using a truth value of true for P, which is what I needed to make the conclusion false, I couldn't also make the premises true. It's valid in that case. I can't come up with a scenario. Okay. Wow, I think we got through everything. That is lecture 5, truth functional logic. We've gone through, you know, general basic remarks, talked about the basic ingredients, claim variables, truth functional operations and their symbols, truth tables, and so on. We went through the 4 basic operations and their symbols, negation, conjunction, disjunction, and conditional. We talked about the common argumentative forms, modus ponens, affirming the consequent, modus tollens, etc. We've talked about how to use truth tables then to represent arguments and then to also assess them in terms of their validity. And I did that using those common argumentative forms. So hopefully you found this helpful. This will wrap up our more detailed discussion of deductive arguments. And starting then with lecture 6, we're going to wrap up section 2, which is our detailed analysis of deductive and inductive arguments. And then we'll move on to more peripheral stuff when it comes to logic and critical thinking. I say peripheral, but it's still heavily involved, right? But peripheral to arguments per se. We're going to set aside arguments in section 3 and talk about rhetorical devices and fallacies and so on. So the point is that after this section, we'll kind of set arguments themselves aside and explore some other aspects of logic and critical thinking, if you will. But before we do that, though, we still have to do lecture 6 and explore inductive arguments in a little bit more depth. So we'll set aside deductive arguments at this point, and the next lecture we'll transition into a more detailed discussion of inductive arguments. All right, that's it. Thank you. Until next time.